Okay, now we know sample space, events, as well as those set rule, the operations. We're ready to talk about axioms of probability. To get us started, I actually want to talk first about what is a probability and different interpretations of understanding probability. So given experiment and a sample space, like capital S, the curly S here, the objective of probability is to assign to each event, okay, we use A or any other letter here, okay? And we use this notation, which we have seen before. PA, okay, again, stands for the probability of event A, which will give a precise measure of the chance that A will occur. Okay, so we have the big sample space, okay, including all possible outcomes, okay, of that experiment, okay, but we're talking about each event that we're thinking or we can be considering, okay. So just to give you some examples, okay, what will be the probability of A, which is the event of the following different event AS here? For example, someone in this classroom wins the Mega Million. I guess we are going to think it's going to be pretty low chance. Okay, so most likely PA going to be really low, close to 0. Part 2, you spin a quarter and it comes up heads. Okay, so if we know that if it's a fair quarter, a fair coin, then, well, PA, based on our usual knowledge, common sense, we're probably going to say that PA is 50%. Okay. However, if we move to part 3, you spin a quarter and it stands up. Okay, that again is very unlikely to happen. Okay, so then we might think that, okay, PA for that particular event will be quite low, maybe close to 0. Okay, the last one I would ask you here, which we're going to try to answer later once we get to know more about this probability, is what is the probability that at least 2 people in this classroom have the same birthday? You might think, okay, this is very unlikely to happen, okay? And I think sometimes intuition is right, sometimes not. And later, once we get to know more about sharing the same birthday, how to actually get that probability, we can then reevaluate our guess here. All right, so like I said, we're gonna talk about different interpretations of probability. And in this class, we're gonna focus on 2, okay? The first type of interpretation is what we call frequentist interpretation, okay? As you can tell from the name, is based on frequency, okay? So again, we're introducing 2, and there's actually no like final agreement or definite agreement out there, like how we really should be interpreting probability. That's why we really want to introduce you to different schools of thinking, okay? So regardless, as you will see after we get through those interpretations, you will see that those axioms that we're going to cover, which is actually the focus of this topic, will be that regardless of how you interpret probability, those axioms gonna work like no matter what. Okay, so keep that in mind. Okay, so the first interpretation is frequentist. Okay, based on the name, like I said, it's gonna be based on frequency. Okay, so the frequentist interpretation goes this way: the probability of event A is the proportion of times, which is frequency, that event A occurs in an infinite sequence or like a very long run of separate trials of this experiment. Okay, so notice we're talking about infinite. Okay, of course, you cannot do infinite number of times, but think about it going to the infinity. And given that definition, we actually going to express it mathematically here. Okay, so n, okay, in the denominator is the number of times you're going to do this experiments, and we know that the limit goes as n goes to infinity. Okay, in the numerator, it's going to be the number of times A happens, which is actually like the frequency. Okay, you take the ratio, and then PA is defined to be the probability, and it's a frequentist interpretation because we're based on repeating the same experiment for a large number of times, like going up to infinity. We're looking at the proportion of times that A is going to occur. Okay, and if you have taken some statistics course before, you probably know that this will be associated with how people think about statistical hypothesis testing. Okay, so when we get to that, we will talk about it. The second interpretation is the Bayesian interpretation. Okay, some of you probably have heard about the term, and just as a advertisement, we do have a 300 level Bayesian statistics course that after taking this 241 probability, you're able to take that, okay? Because this is a prerequisite. But regardless, Bayesian is really like a way to think about interpretation of probability. Generically, we say that a Bayesian can pick whatever number they prefer for the probability of A, PA, based on their own personal experience and intuition, provided that the number is consistent with all of the other probabilities they choose in life. Okay, so this sounds pretty vague and sounds very subjective. In fact, Bayesian interpretation is a pretty subjective degree of belief. Okay, for the same event, two separate people could have differing probabilities. Okay? So for example, I think tomorrow the chance of raining is like 50%, but you might think, okay, it's 80%, things like that, okay? So this is like, in a generic way, we say that this is a Bayesian interpretation of probability, okay? The Bayesian's view must then, two things, conform to other personal opinions, okay? And also change as new data arises according to Bayes' rule. Okay, so later in the semester, we're gonna discuss how to work with Bayes' rule. But here, we just want to make sure that you know that, well, you can have all kinds of subjective belief, but then they should be consistent, okay? As well as Bayesian view can actually also update your belief given the data that you're able to collect. Okay? So Bayesian interpretations of probability avoid some of the philosophical difficulties of frequency interpretations. Just to give you an example, earlier we were talking about probability of A happens, right? Like here. And then, well, as you can see, and we highlighted before, it was an infinite number of times, so you have to repeat this. So sometimes it's really not feasible, right? Like, well, how am I supposed to flip my coin for an infinite number of times, right? So sometimes it's hard to make sure that like the condition that you're talking about in the frequentist interpretation really can be met, okay? So that's what we mean by here. Bayesian interpretations can avoid some of the philosophical difficulties of frequency interpretations, okay? And as another example, just like what we're talking about, the example of tomorrow's chance of raining, like I said, I think it's 50%, you think it's 80%, but well, can we repeat tomorrow for an infinite number of times? No, tomorrow is only one day, it's tomorrow. So again, probability in the Bayesian sense, which is although subjective, but could avoid some of the difficulty of interpretations in the frequentist sense, okay? So it's actually named after a person, okay? It's a minister and a mathematician, Thomas Bayes, in the 18th century in the UK. And it is largely popularized like in the past few decades by revolutionary advance in computational technology and methods, okay? So like I said, if you go on to take Math 347 Bayesian statistics, you will get exposed to a lot more about how Bayesian statistics is done. But in this course, later in the semester, we will talk about Bayes' rule, okay? Here, we just want to show you a contrast between Bayesian interpretation and the frequentist interpretation in terms of the probability understanding,